Thanks. Good morning, everybody. I'm so sorry. I apologize about my accent. My English is not so good like my Brazilian friends, but I'm trying to do my best. It's strange that I'm here because many years ago, I used to work at the train station in a small city, and I saw the little boy taking pictures from the trains passing. And now I see the guy here studying railroads, crossing overseas and study railroads here. So it's very strange. I'm concerned about my age, right? The age is coming. So 15 years later, I see this guy here. I'm a little bit concerned about that. We're going to talk here about the methodology to try to development compositize. So I need to tell to Mr. Stefan from Munich that you are not alone, because we have the same challenges to try to make some procedures to lab analysis, and so that we're going to talk a little bit. I believe that is going to be a complementation that is exactly that you are saying. Well, according the ARIMA reference, all the components of the track should be checked for get analysis for the tie perform. But the majority of the railroads like to see the elasticity modulus and rigid modulus. And we have another requirements about ARIMA, like real set, single tie lateral push, spikes, thermal parameters, and the lateral impedance. But in the real world, is it enough? We believe that we have some the picture about the structural analysis, but when you're talking about life cycle, in the real world, we see a lot of high dynamic impacts, temperature variation, and track geometries problems happen, especially in the heavy hauls. And how should these elements should impact on the tie perform? Especially when you talk about composite ties, that we don't have a very huge parameters to analyze that Mr. Stefan said. And we have a different kind of design, different kind of length. So how can we prepare the methodology to check this analysis, especially on the future, especially on the around the life cycle about the tie? Braskem decide to keep all the knowledge together, talking about railroad technology, polymers technology, manufacturing process, experimental tests, and modeling simulation. We decided to use some expertise from Braskem. Braskem, for it's a chemical industry responsible for resin, polyethylene, and polypropylene. And we beginning to study using international institutes to check creep, fatigue, and aging. We use the Japanese analysis, the Japanese in 2007, 2009, they described a methodology using time and temperature to check the creep and fatigue. So we use this superpositions to check in different strains about how can you going to perform trying to simulation the future, simulation the whole life cycle. So we use the Hopkins pressure bar on different strains that I told in different temperature, and check to both directions, because we're talking about the fiberglass and it's two different directions for the structural material. So we need to make this, to make the samples using two different directions here to check the performance with them. We use the finite element modeling and to try to understand the perform before going to the track. So we use the ballast box and to validate the simulation, the modeling that we had already done. And after we simulated that and provide that the numbers, the results about, especially about the displacement, the tie performance was okay, we went to the track and make some field tests. The field tests were, the object for the field test is analysis structural deformation, ballast tensions, vertical displacement, and especially about the center bolt performance and analysis. We prepared some strain gauge and load cells under the tie to check the displacement and the tension on the ballast. We implement some strain gauges on the tie and check the vertical displacement here. We got some results after 500 MGTs on MRS road. It's a mine corridor. We're talking about 250 MGTs per year, 36 tons per axle. It's a huge heavy haul company, a lot of volume, and we get 15% of contact area between the ballast and the under tie. The peaks on the ballast was reduced exactly because the interaction between the ballast and tie was much better when you compare with concrete ties or steel tie. When you see the gauge, excuse me, when you see the gauge, after we install the composite tie, we have reduced the delta gauge variation. The blue is before installing the composite tie, and the red line is after. So we reducing the variation here. And another point that we are concerned was about the temperature, the gauge variation by temperature. And you see that was not expressive variation. The design that I told, that's one reason that we say that it's important to have different procedures to analysis, because when you're talking about the plastic, especially the composites, every design should be created. So when we check special some standards like ARIMA, EN, we're not talking about prismatic designs. So how can we do it when you're talking a different design? As you can see here, we're talking about the tie that have a composite here, is fiberglass plus polypropylene, and we use two support blocks under the rails to fix the rails using screws. So we have this cover shape, right? And when you're talking about ARIMA, especially ARIMA standards, you see the bending moments, things like that. We talk especially about E-modulus, but when you have a different shape, the rigid is going to be much important to check. So when I say, as I told you, after 400 MGTs, the high ballast tie interaction is much better when you compare with timber and composite and concrete tie. We measurement the reduction of the center bound occurrence. We get some better geometry design on the track. One proof about it, we reduce 3 times grinding pass, because the gauge stayed in the same situation. So we provide that we should make better grinding performance, because the rail stay in the same position. So it's when we have timber tie, it's normal that we change the gauge a little bit, and we have some movement on the butt of the rail. So we didn't see this kind of movement using these composite ties, so that we believe that we can reduce the grinding program, because we have the same shape on the same geometry. That I'm told of the wheel and rail interface. Adequate track elasticity. We trying to use the same elasticity when you compare the good project on the rail and using timber tie. That our target is using the same elasticity when you compare to timber tie. And we have a much better lateral resistance, because the blocks here, you fill the ballast inside the tie, and we have a very, very good lateral resistance. It's a little bit compared with concrete tie. After any test analysis, when you use the Braskem composite tie, is capable to be tested in any track. This is some installations, some pictures that we installed on MRS. We beginning this project in February 19. We have already tested in 2015, but was not the heavy haul railroad. In February 19, we beginning installation in mine corridor. It's just a tangent. And 2020, we beginning on the sharp curve. We're talking about, let me see if I have a picture here. Oh, no, just the instrumentation experiment. I believe that Mr. Arthur is going to speak a little bit more about those instrumentation. But see here, we got some cell loads to check the ballast performance. We included here some mat to check the area contact, some displacements analysis here, lateral and vertical, strong gauge to check the deformation, the tie deformation, and you see a very similar. Then we compare with our modelings. Yes, train passing using. We're talking about super heavy haul. Remember that it's going to be around 40 miles per hour, 36 ton per axle, and around, I believe it's around 15 to 20 trains a day. Maybe Arthur could correct me. This is that's the turnout that we have already installed last month. We have some piece around 7 meters can use at the turnout. So it's important that we reduce the plates to connect both ties. We remove all these connections. So it's the same long bar that we can use 7 meters and reduce these connections, the plates connections between 2 different bars. So that I told you, we believe that we are prepared to begin testing some samples here in US. We are bring some samples to install it in Braskem terminal in Texas. We beginning this project here using the University of Illinois to support us, and I believe that we are ready. So people from BNSF, CSX, and if you want to test it, I believe that we can provide some samples and check some parameters that we should be checked to test it. And remember that Mr. Stephen said, we are prepared to receive all the recommendation and work together to try to prepare the best parameters, the best analysis to make the correct procedures to test it. Not only the structural material for that time, but to check all the life cycle. I believe that that's going to be most important in project like that. When you're talking about composites, you need to check how the performance about this material for all the life. And so that the life cycle, so that I believe that we are prepared to receive the recommendations and work together to try to understand this performance around all the life cycle. Thanks a lot. Any question? Please.
Every home testing, you have a very unique bottom profile to your product. What kind of tamping procedures do you have to use to get those ties ready? You have to re-tamp over a period of time.
Yeah, very good question. When you measure the ballast tension that I showed here, we see that we believe that we can reduce the temper cycle 3 times that we check with MRS. But to special tempers, it's not be necessary. Only the point here that the design is about this, the lip here that's going to be checked. But on the installation, you need to fill it on the middle. So this is gonna be a challenge for us right now, because it's difficult to do mechanically. So probably handily, sometimes it's important that you make sure that's gonna be filled, like a steel tie, right? We believe, and it's my concern, my point of view, all of the ties, concrete tie, steel tie, composite ties should be tempered like that on the middle, because the tempers, when talking about plaster example, the big ones, they temper just the rails, and it's the chance to have the center bound situation, because you temper here and here is going to be empty. So the ballast, when you have the stress, the ballast flew from the middle. So that's we believe that we should happen like this for any kind of tie designs. Okay, I don't know if I answer your question, but it's a challenge for us. Answer directly. The temper this kind of tie is a challenge for us. We had not too much on the beginnings. The people on the field say, "Oh, but it's a little bit more difficult." But when they do the service, it's flew, you know. Thanks for the question. Another one, please. It's a very good question, because it was my first question when I began for the project. For predictive maintenance, the first thing that you're thinking about is how to fail and when it's going to fail. We don't have a good answer for this right now. We believe we are analyzing with BASF people in Brazil, and should be supported here from the US, about the UV problems. You know, maybe we believe that is going to be more displacement, and we're going to lose in the gauge perform. When we installed in 19, The first, it was in the summertime in Brazil. So we're talking about 400 graus Celsius. And on the winter, we have on the night, it was around 10 graus Celsius and 35 graus Celsius on the day. So it's a huge variance. The beginning is a variation in the gauge. We thought there's going to be a big problem, but it's stabilized. 3 years, the same variation, and it's on the tolerance. But we don't know yet how it's going to fail. That's the reason that we're trying to make the check about all the life cycle, you know, but it's a very good question. In another question? Okay, thanks a lot.